This next part will be the most technical. We're going to return to those r hat and t hat unit vectors and the matter of them rotating over time as your object moves around its circular path. So I'm going to replace the color pink, which I had been using here to indicate vectors, and instead get more specific. We're going to let orange indicate radial direction vectors. So radially outwards, the positive radial direction, we call that centrifugal. The word means center fleeing. Versus radially inwards, the negative radial direction, we call that centripetal, meaning center seeking. Okay, so orange for that direction, and then at a right angle to that, in blue, are tangential direction vectors. So tangent to the circle at every point. That's our t hat unit vector. So suppose we've got an object that moves from this position to that position over a short time interval, a very short time later. An infinitesimal amount of time elapses. So a little dt forward in time, and we go from here to here. So suppose that this arc length here is an infinitesimal little distance that we travel, a little ds, in fact, that we travel over some tiny time interval dt. So here's our fundamental relationship for motion on a circle. This infinitesimal displacement along the circumference, so this infinitesimal arc length ds equals r, which is not infinitesimal, times d theta, the tiny change in angle subtended by this tiny arc length right there. So ds equals r d theta. Okay, so at moment one here, we've got an r hat unit vector pointing outwards. Then by moment two, we see that our r hat unit vector has changed direction slightly. We see that rotation of r hat from this direction to that direction. Okay, so what I want to quantify is that small change in r hats. Let's call it dr hats, an infinitesimal change in this unit vector right here. So a change in some vector is going to be the final vector minus the initial vector, so r2, r hat 2 minus r hat 1. So r hat 2 minus r hat 1. Let's put those two vectors sort of tail to tail. So here they are. Here's r hat 1 and r hat 2. And we see that they have a slight difference in direction based on that slight d theta that we've moved through between those two times. And in our head-to-tail method of adding vectors, we can see that r2 minus r1 will be this vector right here, pointing from the head of r hat 1 to the head of r hat 2. So that vector right there is r hat 2 minus r hat 1. That's what we're trying to quantify here. Okay, now here comes the key analogy. I've got this tiny triangle here, and also this tiny slice of our circle here. My argument is that if d theta is infinitesimally small, then this little slice of a triangle and this little slice of a circle and this very thin little triangle here will be very nearly similar triangles to one another. This arc length, which is curved, becomes very nearly straight when the slice is very small. So this arc length is kind of well approximated by this little straight vector here. So I'm arguing that these triangles become similar as d theta shrinks to 0. So as we're looking over infinitesimally short time intervals. And so if this relationship holds for our slice of a circle here, ds equals r d theta, then if this slice is very nearly a triangle similar to this one, then it also is true that this is like our ds, and this length here is like our r, and then d theta and d theta are the same. So if ds equals r d theta, then r hat 2 minus r hat 1, that is equal to r hat 2 or r hat 1 magnitude. R here would be like the magnitude of r hat 2 or the magnitude of r hat 1 times d theta. So ds equals r d theta. This equals this magnitude times that d theta right there. Okay, so r hat 2 magnitude, or r hat 1 magnitude, well, it's a unit vector, so that's just 1. So this is like our r right there, just 1 times d theta. There's our d theta. And the direction, well, we see the direction of r hat 2 minus r hat 1. It points up like this. So looking over at our circle here, this upward direction is kind of like the average tangential direction between this moment and that moment. You see t hat 1 right here, and then t hat 2 right there. That vector rotated also. So here's t hat 1, there's t hat 2, and kind of right in the middle of that arc, t hat would have pointed straight up, exactly in the direction that r hat 2 minus r hat 1 points. So this direction, this straight up direction here, is the t hat direction. Let's call that our t hat direction. Oh, I didn't color that in. Let's fix that. T hat is indicated in blue here, that little vector pointing straight up. Okay, so the argument based on these similar-ish triangles comes down to this. The infinitesimal change in the r hat vector is equal to d theta in magnitude, and it points in the t hat direction. So the change in the r hat vector points in the t hat direction. Likewise, let's argue about the small change in that t hat vector. Here's t hat 1, here's t hat 2. So the change in t hat 2 minus t hat 1. Okay, so we need this vector minus that vector. I've got that triangle drawn over here. So here's t hat 2 and t hat 1. I've drawn them tail to tail. And so t hat 2 minus t hat 1 would be this vector here, pointing from the head of t hat 1 to the head of t hat 2. That little vector there is t hat 2 minus t hat 1. And likewise, I'm going to argue that this triangle is similar to this triangle, which is very nearly similar to this little slice of the circle right here. So our fundamental relationship says ds equals r d theta, which means that this side here, t hat 2 minus t hat 1, should be equal to the magnitude of t hat 1, or the magnitude of t hat 2, times d theta right there. And I've written that here. So the infinitesimal change in t hat 2 minus t hat 1, that's equal to the magnitude of t hat, which is just 1, times d theta. And then the direction of it, we see it points in this direction, straight to the left. And so on our circle here, between this moment and that moment, straight to the left would be pointing straight in towards the center of the circle. So it's kind of like the midway, the average point along that small arc there, straight to the left is in the negative r hat direction, in towards the center of the circle, the centripetal, center-seeking direction. Hence, I've stuck this on right here. The direction of t hat 2 minus t hat 1 is negative r hat. And so, in conclusion, we've got these two statements, this and this. We found that an infinitesimal change in the r hat vector points in the t hat direction. And likewise, an infinitesimal change in the t hat vector points in the negative r hat direction. And now, if we're moving around that circle over time, we can find the instantaneous rates of change of the r hat vector and the t hat vector. So that would be dr hat dt, and this is dt hat dt. Note that this t down here that I didn't color, that's time, t for time, as opposed to the blue t as in tangential. So the instantaneous rate of change of our r hat vector, we just take this equation, sort of divide through by a dt on both sides, and d theta dt we've already defined as omega, our angular speed. So dr hat dt equals omega, and it points in the t hat direction. Likewise over here, divide both sides by dt, a little time interval. dt hat dt equals minus d theta dt, which once again is omega, our angular speed. So here's what we really want to be able to use. The instantaneous rate of change of the r hat vector is omega times the t hat vector. And the instantaneous rate of change of the t hat vector is minus omega times the r hat unit vector. Here's how we'll use it. Our position vector. We want to take two time derivatives of our position vector r. So r would be this pink position vector here pointing from the origin to the location of your object. And we see that the direction of r is radially outwards. So our position vector points in the r hat direction, and it has a magnitude equal to the radius of the circle. So our position vector is given by this. Its magnitude times the r hat unit vector. Let's take the derivative. So ddt of our position vector, we've already defined that as our velocity vector. And you'll see in a moment why I've got the velocity indicated in blue here. So dr dt, okay, we're doing ddt of this quantity right here. Well, we know that the radius of the circle is constant, so we just need r times dr hat dt. R times dr hat dt. And that's what we went through all this trouble up here to work out. Dr hat dt is omega times t hat. So replace this with omega times t hat, and what we found is that your velocity vector at any moment has this magnitude, omega r, and it points in a tangential direction. Something we already knew, velocity always points in the tangential direction. At all times on your circle, your velocity vector is always tangent to the circle. There's no radial component to your velocity. If there was, you wouldn't be on a circular path. Your radius would be getting bigger or smaller if velocity was pointing at all in towards the center or out from the center. So velocity is purely tangential. And then the magnitude of our velocity vector is our linear speed, v over here, which we've already shown is equal to omega times r. Okay, let's now take the derivative a second time. Let's take this the time derivative of our velocity vector. Okay, so we're going to take the time derivative of this quantity here. And since r is constant, but omega could potentially change with time if we were speeding up or slowing down, and of course our t hat vector changes with time, we're going to need to use the chain rule in taking the derivative of this quantity. Okay, so now our acceleration vector. It's defined as the time derivative of our velocity vector, the instantaneous rate of change of the velocity vector. R is a constant, but we have to chain rule this. So it'll be r times d omega dt times t hat, that's this term, plus r times omega times dt hat dt, that's this term. So we can see that we've got a tangential term and whatever this comes out to be. So this first term, d omega dt, we already defined that as alpha, our angular acceleration. So our acceleration has a tangential component equal in magnitude to r times alpha. And now over here, we need the time rate of change of your t hat unit vector, which we worked out back up here. dt hat dt equals minus omega r hat. So this gets replaced with minus omega r hat. And so we see that our acceleration has both a tangential component. This is our tangential component here, a sub t. And it has a radial component, a sub r. And our radial component has what we'll recognize as a familiar form, minus omega squared r. This is our centripetal acceleration. Okay, let's pause for a moment, pick up from there.